Now with the squirrel and the harmonic oscillator potential, it is observed that the first three magic numbers 2, 8 and 20 are reproduced, but the rest are not. Now to reproduce the rest of the magic numbers, that is 28, 50, 82 and 126, N or Z, the spin orbit interaction is included with the central potential. Now, as it is well known that the nucleons are the spin half particles, and there is a very strong interaction between the spin and the orbital angular momentum. Spin and orbital angular momentum. If this spin orbit angular orbital angular momentum interaction is added to this potential, then it is found that they have the ability to produce these magic numbers, only this is not reproduced. Instead of say 126, a large gap occurs at 114. But with some modification in the potential, if the shape of the potential squirrel or harmonic oscillator is slightly changed, then this can be made produced. Now, the spin orbit interaction is written in this form, that is V, the spin orbit interaction is written as VSL. F of R is a potential function L dot S. L is the orbital angular momentum, S is the spin. Now Fr is the L is the orbital angular momentum, S is the spin, momentum, and Fr is a potential function. With the inclusion of this potential, if one calculates the energy level, then it is found that the large energy jump to the energy level occurs after say 2, 8, 10, 20, 28, 50, 82 and 140. But after that, with some modification in the potential, the 126 can be reproduced. Now, because of the strong coupling between these two, L and S, because of the strong coupling between L and S, it gives the total angular momentum J, this J is equal to, there is L plus S. Vector sum. Now, if we square both sides, that is, if we write this one J square, L square by L dot S. Now, from this expression, one can find the L dot S product. The numerical value or the eigen value of this J square, we write J into J plus 1, it is L into L plus 1, S into S plus 1 plus twice L dot. Now, from this expression, the product L dot S, which is used in the potential expression, can be found out. Now, we know that the spin S is actually half. Therefore, when your J value, this is equal to J is equal to L plus S. Therefore, if J is equal to L plus minus half, once you consider L plus half, put in this expression and find what is the J, and once L minus half. Okay. Now, therefore, for these two, either J is equal to L plus half or L minus half. Now, by inserting the values, either J is equal to L plus minus half. In this expression, one can calculate L dot S for two possible cases. Then L dot S, that will be equal to half into small l, or J is equal to L plus half, and another is equal to minus L plus 1 half, it is half L plus 1 for J is equal to L minus half. Here, not for, it is not valid for L equal to 0, because if L equal to 0, then here you get minus half, so which is not possible. So this is not valid for L equal to 0. Therefore, we get two values of L dot S, one is half L and this. Now, therefore, the difference between the potential in these two cases will be equal to the difference in potential energy between these two cases is delta VSL, delta VSL. That is equal to half FR into 12 plus 1. That is this minus this, half L, with L. therefore this spin orbit interaction potential is included in the calculation. The effect of this spin orbit potential is analogous to the fine structure splitting in the atomic physics. In atomic physics, when magnetic coupling is there, the degeneracy is removed, the levels are splitted. So here also it has the same analogous effect, that the spin orbit interaction when included, the degeneracy is removed and the levels are splitting. The effect of such a spin orbit is analogous to the effect of magnetic coupling in fine structure splitting in atomic physics. The inclusion of this spin orbit coupling can reproduce the magic numbers. Now with this inclusion of this spin orbit coupling, it is observed that the large energy jump occurs at 2, 8, 14. Although 14 is not a magic number, but here 14 comes. 28, 50, 82 and 114. 14 is coming, it is not a magic number, and 114 instead of 126. Now, so it can produce 2, 8, 20, 28, 50, 82, all these numbers except this 114. So, it is concluded that by certain modification of the potential, that means if we slightly change the shape of the, say, either square or harmonic oscillator potential, then this 114 instead of 114, 126 can be reproduced. Now, the most important is that these calculations have reproduced a level sequence such that the neutron or the proton numbers (28, 50, 82 and 126) along with the other numbers, that is 28 everything, along with which is reproduced by only the square wave and harmonic oscillator 28 these occur at completely field states. That means when the levels are filled, different neutron and proton energy levels are there. Each level can contain say two, either neutron or proton. So in these numbers, either Z or N, the cells are completely filled. So next, if we add one neutron, this neutron will occur here. In the next higher level, so a large jump occurs in this case. So suppose this is a here 6 proton, 6 neutron, and this is suppose a carbon 13 or say neutron is added here. So here the last neutron will go, there will be large energy jump between these two. So in case of first say oxygen, here 8, oxygen 16, 8, 8, so even with nuclei. Next if we add say another proton or neutron, either oxygen 17 or say fluorine 17, then you get the last proton or the last neutron, that is a large difference between these field states and this one. So up to this, these are very strongly bound. Now, therefore, with this number, the cells are completely filled, the closed cell, and these numbers, they behave as the inert gases in atomic physics. Okay. Now, but this 126 is not produced. Instead of 126, 114 comes. So with some modification in the potential form, so one can reproduce this one instead of 114. So instead of 126, actually 114 is reproduced. And by certain modification in potential, the number 126 can be produced. Now, if we draw the level sequences with the spin inclusion of the spin orbit interaction, suppose this is 0, 0 is the energy level, this is 1s, you get 1s half. In the S state you get only 2 nucleons. So here you get total number 2. Now then here it is 1h cross omega. It has an odd quality, so it is 1p. So this 1p level will split one p 3 by 2. You get here 1p half. By 2, 12 plus 1 or pj plus 1 number of particles. So here you up to this you get 6, up to this you get total 8 numbers. Then you get 3h cross by sorry 2h cross omega. Parity is written here. You get say here 2 levels. One is 1d and this is 2s. This is 1d 5 by 2. 1d 5 by 2. This is S state. 2s half. And this is 1d 3 by 2. state always comes lower for a particular value of L. So here up to you get the total number is 12 plus 1, 5 by 2, here you get 6, here you get 2, and 3 by 2, here you get 4, 2j plus 1. So up to this, you get 8 plus 2, say here you get, 8 plus 6, 14. 16, and here you get 20. This is another completely filled states up to this. Then you get here 3h cross omega. Here you get 1s. And 2p. So this 1f will be splitted into 2 and here this is F state. So higher spin state will be lowered. Is the F7 by 2. 1 F7 by 2. This is P state. You get 2P3 by 2. The higher spin state always comes lower. This is 7 by 2. So this is 1 F5 by 2. And you get 2p half. So 7 by 2, so here the total number will be equal to your 8. 7 plus 1, here you get 4, here you get 6, here you get 2. So up to this first, here you get 20 plus 8. 28, 32, cumulative, 38, 40. And after that, for each cross omega, now here we get 3 levels, 1G, 2D and 3S. 1G, 2D and 3S. Now 1G level, when it is splitted, here you get 1G 9 by 2 and this is 1G 7 by 2. And this 9 by 2 means here you get 10, then the 50 will appear here. In this way, the sequence goes. There is no space to draw. Then after that you get 5H cross omega. And in the 5H cross omega, when the 5H cross omega level will come, here you get 1H, 2F and 3P. 1H, here you get H 11 by 2, 9 by 2. Here also F you get 7 by 2, 5 by 2, and P 3 by 2 and half. Okay. So next all the levels will produce. So with some modification with the inclusion of the spin orbit interaction, it is found that this 2, 8, 20, instead of here also the 14 will also appear. 2, 8, 14, 20, 28, 50, 82 and 114. But if we modify the potential slightly, the central potential, the square or harmonic oscillator, then instead of 114, 126 can be reproduced. Now, so it is found that the cell model can predict all the magic numbers with the inclusion of the spin orbit interaction. Now, when the cells are completely filled, suppose here, now there all the neutron and proton energy levels are filled, either n equal to 8 or z equal to 8, all the levels are filled. So, when the next neutron or proton is added, then the ground state spin, for the completely filled states, the ground state spin and parity will be equal to positive parity and zero spin, total angular momentum. There is no exception to this rule. Now, when the another proton or neutron will be added here, then the ground state spin and parity of that nuclei will be completely determined by that single unpaired nucleon. Okay. Now, so there are certain rules to find the ground state spin and parity of the nucleus. The following rules are applicable to determine the ground state spin and parity. The first one, the even nuclei. Even nuclei. That is for nuclei for which Z and N are even. For even nuclei, that is nuclei with even N and even Z, even N and even Z have total spin J is equal to 0 and parity is positive. So it is written sometimes J plus is equal to 0, that is and there is no exception to these rules. Whenever you see any heavy nucleus, oxygen 16, or say carbon 12, or calcium 20, so it has the ground state being 0 and the parity is positive. Now next is odd nuclei. That is either Z is odd or N is odd. An odd nucleus that is either N is odd or say Z is odd. It will have total spin, obviously ground state spin, which is equal to half integral angular momentum then L will be either L plus S or L minus S, because the ground state spin and parity will be completely determined by the single unpaired nucleon, and the parity is we know parity is minus 1 to the power L. In which angular momentum state is that? If it is in P state, it will be negative. If it is D state, L equal to positive in this way, according as the value of L, even or odd. But there are some exceptions to this rule. It is not always true. There are some exceptions. To this rule. Now if you consider say oxygen 17, then oxygen 17 will not have its ground state spin 0 and parity positive, because here N is 9. For oxygen 17, N is equal to 9. So up to 8, the total spin will be equal to 0. The last single unpaired neutron will determine the ground state spin and its parity, because it is an odd nucleus. Now, and for odd nuclei, it is both the neutron and the proton numbers are odd. For an odd nuclei, that is N is odd and Z is also odd. Then in that case the ground state spin will be the vector sum of the two unpaired nuclei. After filling the states, a single unpaired neutron will be here, a single unpaired proton is here. So the total spin will be equal to, here it is Jn plus Jp, and the total parity will be equal to minus 1 to the power in which state they are Ln plus Lp. Now therefore for ordered nuclei the ground state spin is the vector sum of the unpaired or single neutron and proton. As it is written here, vector sum of the unpaired neutron and proton. That is, in that case, the ground state spin will be equal to your Jn plus Jp, and the parity is minus 1 to the power Ln plus Lp. So with the help of the cell model, not only the magic numbers are reproduced, but the ground state spin and parity of the nuclei can be explained. So this is the more important observation of the cell model. It is not only the magic numbers to reproduce, but to determine the ground state spin and parity of the different nuclei. But there are certain exceptions are there. If we calculate nitrogen 14, 7 ordered nuclei, its ground state spin according to cell model, it does not match with the experiment. It is something different value. So there are certain exceptions for ordered nuclei. There are certain nuclei for which this cannot be reproduced, because for those nuclei which have very large quadrupole moment, they cannot be predicted by this cell model. Because why? The question is why it is not produced, because the cell model is completely based on the spherical symmetric potential. The harmonic oscillator, square L, or have spherical symmetry. But the nuclei which has a large quadrupole moment, that is large deviation from the spherical symmetry, for those the cell model predictions are not correct.